Hi again. This is problem number 49 from the same chapter, chapter 23. If you haven't read that, now is the time to pause the video and turn to the page and read the problem. So here we are looking at the electric field at R equals to 0. So at R equals to 0, that means right over here. Now I am marking the center point, and clearly we are using the Gaussian law, electric field E dotting to dA. Whenever we are looking for an electric field, at least under this chapter, we are looking at using the Gauss's law, because that is really convenient. And then you have Q enclosed divided by epsilon, and when you look at that point, there is no Q enclosed, there's no enclosed charge. As a result, let me write it, Q enclosed equals to 0. As a result, we end up with E equals to 0 at that point. That's easy. And then we have part B. Part B, we are looking at the electric field at R equals to A divided by 2. Now this is an interesting problem, and remember the solid sphere of radius A equals to 2 centimeters. That's how the problem is stated. So if it is a solid sphere, well, let me mark that using this. So this is the solid sphere. Oh, my A was cancelled out. Okay, I'm going to rewrite that A over here. That's the radius. So the solid sphere, that doesn't mean it is a conducting sphere. It is just a solid sphere. I hope that you all remember my M&M example that I discussed in the class. So keep that in mind. And now we are going for R equals to A over 2 location. Now the practice is to go to R equals to A by 2 location, and then we are drawing the Gaussian surface. Now in this case we are dealing with the spheres, and the easiest Gaussian surface for this case is a sphere. So I picked a sphere, and okay, and I am going to write the Gaussian law, the equation E dot dA equals enclosed Q over epsilon naught. Now the solid sphere has a charge of Q1 5 femtocoulomb, and the entire sphere has 5 femtocoulomb. Now in order to find the enclosed Q by the Gaussian surface that we drew, the Gaussian sphere, we have to use the ratio rule as we discussed in the last class. So entire sphere radius is A, so the volume is 4/3 pi r cubed, where r is A, and the charge enclosed in that sphere is Q1. If you want to find the charge in the enclosed area, we have to get the volume of that area, which is 4/3 4/3 pi, and the corresponding radius, in this case it is A divided by 2 and the cube of that. Now please pause the video if you want to, and then find out what I am talking about here. This is related to, very much related to yesterday's class. Okay, so electric field is a constant, so I take it out, and then the loop integral dA, and enclosed Q, we found the enclosed Q over here, so let me write down that over here. So you got the Q enclosed, or the uppercase Q if you like, and then let me separate that. So enclosed Q equals to Q1, and the 4/3 cancels out, 4/3 pi and pi cancels out, and a to the power 3 and a to the power 3 also cancels out, and here you will get q enclosed equals q1 divided by 8. So coming back to this, enclosed q is q1 divided by 8 divided by epsilon, and E, area of the Gaussian sphere that we are looking at, area of a sphere is 4 pi r square. So here you got 4 and pi, and r square is a over 2 and the square of that. So this 4 and the 2 to the power 2, those two will cancel out, and you will have the electric field at the point given by q1 over 4. Actually there's no 4 now, let me erase that. There is 8 coming from here, 8 pi a square and epsilon naught. This is the final answer. You have the value of q1, and you also have the value of a, and also you know the value of epsilon, so you can substitute the values and get. So part C, the problem wants us to find the electric field at point A, and here goes part C. Actually I'm going to use the black pen. So when you draw the Gaussian sphere, that's our practice, that would be lying on top of the inside solid sphere. So that's the Gaussian sphere. So it covers the entire charge on the solid sphere, which is a q1, and let's use the Gaussian equation, Gauss's equation. E dot dA equals q enclosed. Sometimes I write uppercase q, sometimes I write lowercase q, that's no big deal. And the electric field is a constant, and you remember, I don't have to repeat, E field and the area vector, they are parallel to each other. So when you expand the dot product, the cosine theta becomes cosine 0 and it goes away. I don't think that I am completely ignoring the vector dot product here. We talked about it in the last video too. So this is what we have. Enclosed q is q1 over epsilon naught, and area of the sphere is 4 pi r square. R is a, so there we go, q1 over epsilon naught, and the electric field at point A is q1 over 4 pi epsilon naught and a square. This is kind of a familiar form for us, and that's our answer for part C. And for part D, now we are looking at a distance 1.5a. Now again, the practice is to draw the Gaussian sphere. You can see that we are following some kind of a recipe here. Now 1.5a, it is less than the b. B is 2 times a, I think. And then here goes the Gaussian surface, and Gaussian surface in this case is a Gaussian sphere, and let's look at the electric field. Same drill. E dotting to dA, q enclosed over epsilon naught. Now E constant, and I am going to substitute for a so that I can save the space, and that's going to be 4 pi r square, where r is 1.5a, and the square of that is the area of the second Gaussian surface, the second Gaussian sphere, and then the q enclosed. Now q enclosed is the enclosed charge by that sphere. As you can see, there's only one thing inside, and that one thing inside is the solid sphere that I am painting right now. That is the only thing that we have inside as a charge, and then as a result you can say that the enclosed charge there is simply q1 like before. So what is different here? You will see the difference is that oops, I forgot about the epsilon naught. So here you have q1 and 4 pi times 1.5 and epsilon naught a square. This is the answer now. So if you compare the two, the first the answer we got for part C and the answer we got for part D answer is smaller than before, because here we have an additional 1.5 in the denominator, so the denominator is bigger than before. So this E field, as we expected, is smaller than the previous one. I'm going to draw a line to separate this because part E is pretty straightforward and easy, and also part F. Oops. So here we go, part E. We are looking at R equals to 2 by 2.3a distance, and if I draw the Gaussian surface there, that actually lies right inside the conducting shell, in between the inner and the outer radii. So clearly a conducting shell does not have any conductor, does not have an electric field inside. As a result, we get E equals to 0, and that is our answer. And for part F, now we are looking at R equals to 3.58 radius, and I'm going to draw my last Gaussian surface for this problem. There, and the same drill, E dotting to dA equals Q enclosed and divide by epsilon naught and E times 4 pi r square. That would be 3.5 a and the whole thing square equals Q enclosed over epsilon naught. Now here you have a place where you need to be careful on finding Q enclosed. So at this point the enclosed Q, let me write it here, Q enclosed equals to Q1 plus Q2, but if you check you will see that Q2 is minus Q1. As a result, you have an enclosed Q equals to 0. As a result, you have the electric field outside this system, the shell, and the solid sphere is also a 0. So take your time, pause the video as you need, and then try to understand. You should understand at this point that we are repeating the same thing over and over. Okay.